Thank you so much, Kelly. So as Kelly mentioned, my name is Lauren. I am a staff scientist here at Argonne in the Applied Materials Division. My work in particular focuses on separation technologies. So for those of you who have heard terms, like reverse osmosis or maybe capacitive deionization, these are some of the separation technologies that I work on for a number of different applications. Some of those applications include bioenergy in particular. Actually, a large portion of my work that's currently funded is focusing on bioenergy technologies. So that's why Kelly invited me here today to speak to you to give essentially an overview of bioenergy. So to start out, I wanted to start out with this number, 5.6 billion metric tons. 5.6 billion metric tons is the amount of net greenhouse gas emissions that were emitted in the US alone in 2021. So I know that at this point, this is really just a number. Just to kind of put this into context for you, that this 5.6 billion metric tons is equivalent to 56,000 fully loaded aircraft carriers. For example, the aircraft carrier that you see in the photo here. So 56,000 of those fully loaded aircraft carriers with planes, all the equipment, everything. That's how much greenhouse gas emissions the US is emitting in a single year. So for this reason, decarbonization has really become a global priority, a global priority as a strategy to mitigate climate change. In thinking about how to decarbonize, first we need to understand where emissions are coming from. As you can see in the pie chart on the left-hand side here, the transportation sector is one of the largest contributors to greenhouse gas emissions in the US. In 2021 alone, the transportation sector accounted for 1,800 million metric tons of carbon dioxide equivalent emissions. So that's a huge number when it comes to transportation alone. The primary driver of transportation-related emissions is combustion of fossil fuels. The transportation sector, as you can see in the pie chart, is closely followed by industry over here. Industry includes manufacturing, and within manufacturing you have petroleum refineries, chemical productions, and both of those two represent the majority of energy use. So on top of the combustion of fossil fuels, we have the production as another major contributor to greenhouse gas emissions. With aggressive greenhouse gas emission targets economy-wide, the Department of Energy and specifically the Bioenergy Technologies Office have really put an emphasis on a sustainable bioeconomy. The sustainable bioeconomy is going to play a very critical role in achieving the aggressive greenhouse gas emission targets that the administration has set forth. So with these aggressive greenhouse gas emission targets and the role of the sustainable bioeconomy, I do want to point out that there is currently an underutilization of biomass and potential bioenergy resources. In fact, if we were to leverage more than 1 billion tons of sustainable and domestic biomass that's available to us in the US, we could produce 60 billion gallons of low-carbon biofuels and 75 billion kilowatt hours of renewable electricity. Or if that entire, instead of biofuel, if all of those resources were devoted to the production of renewable hydrocarbon-based chemicals, we could produce over 200 million metric tons of renewable chemicals and materials. So there is a huge potential for bioenergy, bioproducts, biofuels, biochemicals. But more importantly, by converting these renewable carbon resources into fuels, into electricity, into chemicals, this could save or it could reduce carbon dioxide emissions by 450 million metric tons per year. So what exactly is bioenergy? Bioenergy, biomass, is one type of renewable resource that can be converted into liquid fuels, known as biofuels, for transportation, for heat and electricity, or for products. So depending on what the end product is here, we may refer to that as biofuels, biopower, or bioproducts in the case of chemicals and materials. When it comes to biofuels, biofuels include things like cellulosic ethanol, biodiesel, and renewable hydrocarbon drop-in fuels. Essentially, drop-in fuels mean that they're compatible with existing vehicle fuels, so you could literally drop them in as a substitute or as a replacement for conventional fuels. The two most common types of biofuels that are in use today are ethanol and biodiesel. Biofuels can be used in airplanes, in most vehicles that are on the road, so they're a very important energy fuel source. And renewable transportation fuels are essentially functionally equivalent, as I mentioned, this concept of drop-in fuels. They're functionally equivalent to petroleum-based fuels. Biopower technologies essentially convert biomass resources, biomass fuels into heat and electricity using processes like those used with fossil fuels. But there are three ways to kind of go about this. One would be actually burning, the second would be bacterial decay, and the third would be conversion to a gas or a liquid fuel. So that's kind of the category of biofuels. And then bioproducts, as we had mentioned on the previous slide, if we were to take these renewable carbon resources, actually convert them into any sort of intermediate, we can essentially take those intermediates and then we can produce chemicals, fuels, polymers, whatever it may be, that are functionally equivalent. They're versatile, just like any petroleum-derived products. So we kind of have these three different categories of bioenergy here. Most importantly, when it comes to bioenergy and the resources that we have available, the abundant and renewable bioenergy sources that we have can help us by contributing to a more secure, sustainable, and also economically sound future, because as I think we're all aware of, these can help us to provide clean energy sources, help us to reduce dependence on foreign energy sources. They can also generate U.S. jobs. The one important component that I left out on the previous slide was the many jobs that could be generated through the use and the development of bioenergy resources, and then revitalizing rural economies. So it's great. We talked about bioenergy, we talked about what it is. When it really comes down to it, it's an extremely complicated process. I don't expect you to digest all of the details that are in this block diagram that's shown on the screen here, aside from the fact that it is an extremely complicated process and there's not a single path for you to go from renewable carbon resources on the left-hand side to final fuel products power on the right-hand side. There are a variety of steps that can be combined in an endless, essentially, number of combinations in order to go from a starting material into a product. So altogether, this is extremely complicated. It's not something that can be handled by just a single national lab. So although I am going to talk to you in a couple of minutes about Argonne's role in this space, I want to take a step back and talk about all of the national laboratories. So I don't know if Kelly, if you had gone over any of this in your morning talk, but Argonne, as you can see here, is actually one of 17 DOE National Laboratories. Is everyone from the Chicagoland area here, or are people from across the country? Okay, great. So I'm happy that I showed this slide with all of the different national labs and kind of where they're spatially located, because you may start to notice that there are other national labs that may also actually be active in the bioenergy space that are close geographically to where you are. So Argonne, located here, is again one of the 17 national laboratories. My work in particular, on a daily basis, I'm working from researchers from Pacific Northwest National Laboratory, Lawrence Berkeley National Laboratory, National Renewable Energy Laboratory, which is near Denver, Los Alamos National Laboratory, Oak Ridge National Lab, but that's, just to name a few. But there is a very robust portfolio of national laboratories and research that is ongoing across the country. So a little bit more about the specific history of Argonne in particular. Argonne was actually established as the nation's first national lab in the 1940s. Argonne was founded with a mission to develop utilities or tools for nuclear power. So you can see kind of this picture here. Maybe some of you have also seen Oppenheimer and maybe seen some references to Argonne and to some of the other national labs there. That's essentially where all of the national labs were kind of born out of. Just to give you a little bit of idea, a little bit more background information about Argonne and about who we are and what exactly we're doing. Argonne has, as you can see here, over 3,000 full-time employees. We do have science and technology staff. We have postdoctoral researchers. We have joint faculty that may have joint appointments, including myself, with local universities. For example, Northwestern University, University of Chicago. We actually started a new joint appointee program with the University of Houston. So again, even if you're not necessarily local, there may be some opportunity, depending on the universities that you are from, for you to actually have a joint appointment with Argonne if that would be something that you are interested in. In addition to that, we have close to 6,000 facility users. So I'll talk in a couple of minutes about some of Argonne's user facilities, but these are essentially people from all across the country and even world, in fact, that are coming to use Argonne's equipment and tools. I also want to note here that we have 1,000+ students. So as all of you are instructors, students play a very critical role in our research and development. We actively, including myself, have summer students that come to work in our labs every summer. They work on real research projects. They contribute to our milestones. They help us to publish papers in some cases. So just something to keep in mind as far as opportunities go for your students. We are happy and welcome to offer research opportunities for high school students, undergraduate students, graduate students, and then as far as PhD students and postdocs, they would kind of fall into this category. But for students, there are a number of opportunities. And so if you have students that you may think are interested in some type of opportunity, I would encourage you to reach out to either Kelly or other folks in our student programs office. They can certainly provide more details about these opportunities. I just want to emphasize again that students play a really critical role, and we really welcome that opportunity for. So as far as Argonne's strategic initiatives and kind of the portfolio of research that Argonne covers, you can see some of the overarching topics that we're working on. We are not only working on bioenergy. In fact, you don't even see bioenergy specifically called out in one of our strategic initiatives. It does fall into the decarbonization, which is why I wanted to provide a little bit of introduction on decarbonization and what that means and how it's related to bioenergy. The other one that bioenergy and biotechnologies are related to is the circular economy. Essentially, figuring out how you can make use of products at the end of their life for a second use, reuse, recycling, that kind of thing. So bioenergy is highly relevant and related to two of the strategic initiatives here. But again, those are 2 out of the 8 initiatives that you see on the screen. So more broadly and a little bit beyond that, we have expertise in artificial intelligence for science, in autonomous discovery. You can see some of the robotic platforms here, climate change and climate action, circular economy we talked about. X-ray science is another big one with Argonne's advanced photon source. Decarbonization we talked about. Imaging and detection, again, this is really enabled through some of our advanced characterization tools at the Advanced Photon Source, Center for Nanoscale Materials, both of which are Argonne user facilities, and then radioisotope discovery. So speaking of the user facilities, our national user facilities really do help us to accomplish our work. You can see the 6 user facilities here. 5 of these facilities are funded by the Department of Energy's Office of Science. So you have the Advanced Photon Source, which is essentially an accelerator facility that allows us to do all sorts of characterization of the properties of materials. This is really beneficial in the context of bioenergy. It's really beneficial for the development of things like catalysts, separation materials. If we want to study fundamental phenomenon, reactions that are happening, kinetics that are happening with different catalysts, we may use the Advanced Photon Source for that. The ALCF, Argonne Leadership Computing Facility, is a supercomputing facility that may be helpful or is helpful when we want to simulate what's happening experimentally, whether that be for predicting what may happen so that we can avoid doing experiments. As you know, if you've done experiments in the lab or maybe taught a lab class, experiments can be very time consuming and don't always go as planned. There's always unpredictability and uncontrolled, things that happen when you try to do experiments. So we may have an advantage if we try to simulate some of these things in order to predict and kind of forego those experiments. We may also use computing to actually understand what's happening. So even if we've done an experiment and all has gone well, we may want to be able to have a better understanding theoretically of what's happening in a particular reaction, a particular process. And so we may use computing to kind of understand after the fact. Another one that I use quite often is the Center of Nanoscale Materials here. The Center of Nanoscale Materials has a wide array of analytical equipment. So microscopy, spectroscopy, these things are really helpful for understanding various properties of materials. Again, I'm thinking about things, for example, maybe fuel products or separation materials. I'm going to keep coming back to separation materials because that's my expertise. But again, catalysts, or if we need to characterize various biomass feedstocks, products, intermediates, there is a very wide array of tools here that can help you to characterize elemental composition, chemical properties, physical properties, you name it, and there's probably a tool there that can help you do it. So kind of going into Argonne's partnerships a little bit more, Argonne has a very wide network of industrial partnerships. You can see, just from the logos here, that collaboration is a very important part of our work here. We are trying to do work, that is industrially relevant in terms of the solutions and the technologies that we're developing. So all of our industrial partners play a very critical role in our research and development, essentially from the beginning of processes. So we've made, really extraordinary advances across the board, from artificial intelligence, grid engineering, material engineering, quantum information, all in collaboration with some of the industry partners that you see here. So now that we've kind of gone away from bioenergy a little bit, I want to come back to the bioenergy aspect of things. And to start that, I actually want to play this video that I think gives a very nice, I think this gives a very nice overview. I'm not sure if I can make it bigger, but I think that this should be okay if everyone can see it in the back. A nice overview of bioenergy.
Biomass. It sounds complicated, but really it's simple. Biomass can be defined as any organic material or waste that contains chemical building blocks like carbon, hydrogen, and other components that are vital to our modern energy and materials economy. Biomass is the single largest supply of carbon on planet Earth and is a sustainable and renewable source for the products that are currently made from petroleum. Here's how it goes from waste to watts. Trees and plants absorb energy in the sun through photosynthesis. The energy is trapped inside until the organic material is converted into other products that are used as sources of energy and materials. There are several kinds of biomass, such as agricultural residues, purpose-grown energy crops, and wood. And for hundreds of thousands of years, humans have used wood or charcoal made from wood for fuel to heat homes and cook food. To make bioenergy's wood, scraps or sawdust can be collected from farms and forestry manufacturers. There are several ways to convert biomass into usable energy. It can even be turned into fuels to power cars, trucks, and airplanes. To make fuel, one is converted first to an intermediary gas or liquid, and that can be upgraded to make a final product such as gasoline, diesel, and jet fuel. It's almost like putting a tree trunk in your gasoline tank. Biomass also includes wastes. There are processes that work for many types of waste biomass, like animal waste. That's right, poop. Believe it or not, poop can be used to make electricity. Manure from farm animals, mostly cows, is put into a big tank called a digester. Like your own gut, a digester has bacteria that eats waste and turns it into methane gas. The methane is burned to heat water. The hot water produces steam. The steam creates pressure that spins a rotor inside a turbine. The turbine powers a generator, and the generator produces electricity. And that's it. Methane can also be captured from landfills. When biomass decomposes, it emits a gaseous product called biogas. Biogas is rich in methane, and after some cleanup and upgrading, The methane gas can be captured and burned in the same process to make electricity or to heat your home and cook your food. Biomass can also be used to make products like polymers and plastics that are made from renewable sources of carbon and are either recyclable or biodegradable. This will help solve the problem of plastic waste. Yes, biomass isn't so glamorous, but it is a clean, renewable source of energy and materials that are essential to a modern society. Who knew waste could be a powerhouse?
So this is actually a video that was developed by one of our sister labs, the National Renewable Energy Laboratory, which is near Denver, Colorado. I wanted to include this because I think it gives a very nice overview of what bioenergy is, some of the different possibilities. If you have specific questions about any of the processes, starting materials, or products that you saw in that video, I would be happy to kind of answer them for you. But in the meantime, with a 30-minute presentation, I thought that provided a nice high-level summary of some of the different opportunities and also pathways. So coming back to Argonne's specific role when it comes to the bioenergy, and the bioeconomy, you may see this acronym on a couple of my slides, BETO. BETO is the Bioenergy Technologies Office. So Argonne has a pretty robust portfolio of research and development that's funded by the Bioenergy Technologies Office. The Bioenergy Technologies Office is also the office within DOE that is supporting the Bridges workshop that you guys are all at today. So in addition to research and development, there's a lot of emphasis on, education, not only for students, but also instructors, as we're all here today. So when it comes to research and development, Argonne's vision for the Bioenergy Technologies Office is really to leverage our competencies in modeling. So whether, most often that's computer-based modeling, and technology development to enable a low carbon and environmentally friendly economy through integrated development. And you see these keywords again, the biofuels, bioproducts, and also ecosystem services. So in the figure that you see on the right-hand side, you can see a lot of the topics that I've kind of been casually mentioning throughout this presentation. You see some of the products and some of the concepts on the outside. Methane we saw as a product in the previous video. Organic acids are another intermediate that would be produced as the result of bioconversion processes. This is actually separation, so separation-related materials, electrochemical separations and adsorption-based materials as examples. The GREET model, which many of you may be familiar with or may have heard of, the GREET model is a life cycle assessment tool that is really gaining popularity, especially recently for the evaluation of sustainability or environmental impacts. So the GREET model is capable of calculating or evaluating greenhouse gas emissions, water consumption, energy intensity of various processes. So if sustainability is something that you're interested in, I know even the educational team here has developed a number of activities that are kind of based off of and leverage the GREET model. We also have a number of other tools, for example, those that are related to water resources and ecosystem services. When it comes to biopower, again, this is kind of just a little bit of a different topic, using these biomass-based resources to produce heat and power as opposed to biofuels or bioproducts. But we're also doing work on catalysis and microbial strain development. And then circular economy, we talked about these concepts of reusability, recycling, and kind of end of life of products. So we do have, a range of projects related to materials, process development, scale up of different technologies. We are doing, not only experiments, but some of our work is data-driven and also cross-cutting for these different activities. So these efforts altogether are really intended to accelerate the deployment of technologies from bench scale. Normally bench scale is like smaller scale up to pilot, and then larger scale that can eventually be deployed at commercial or industrial scales, and help the Bioenergy Technologies Office meet their key targets related to greenhouse gas emission reductions or sustainable fuel development. Outcomes of our efforts at Argonne. support U.S. global leadership in advanced bioenergy and economic competitiveness, enhancing energy security, consistent with the Bioenergy Technologies mission. So to go a little bit more into detail into some of the specific efforts and where exactly Argonne is playing a role, we talked in the beginning about decarbonization of the transportation sector. So the transportation sector includes all modes of transportation. It includes aviation, it includes marine, and it also includes vehicles that are driving on the roads. So when it comes to the particular sectors that you see here, and then sustainable aviation fuels is going to be on the next slide, there's a lot of emphasis and a lot of focus on these sectors in particular, marine, aviation, and the rail sectors, because these are traditionally considered difficult to decarbonize. We all have seen, the increasing number of electric vehicles on the road, but what we are not currently seeing is we are not seeing electric planes. So that's what we mean by I said hard to decarbonize before. I mean hard to electrify. So these are traditionally considered the difficult to electrify sectors, where it would be very difficult to put an electric driven or a battery powered vehicle into play into any of these sectors. So ships, for example, marine that you see on the left-hand side here, we are playing a role in terms of development of tools, as well as studying the techno-economic life cycle and feasibility of biofuels for the marine sector. Essentially, this is evaluating the economic and sustainability implications of different biofuels. It's one thing to be able to produce a biofuel, but in addition to that, as we all see with products in our everyday life, in addition to developing a product, that product often has to be cost competitive with other, in this case, petroleum derived products. And as sustainability concerns are becoming, or issues are becoming more and more at the forefront, we also want to make sure that the technologies or the products that we're developing have less environmental impacts in comparison to petroleum derived products. As far as the rail sector goes here, again, we are really focusing on assessing various solutions for rail, their technical and economic feasibility to ensure cost competitive with potential other solutions. These types of analyses are also critical for identifying bottlenecks in processes. For example, we can identify either key cost drivers or key sustainability drivers so that we may have a better understanding of where we should focus our research and development. If there's one key driver of the cost, we'll go ahead and use that information to direct additional focused R&D on that particular topic, as well as kind of understanding risks that are associated with the process. So this type of techno-economic analysis and life cycle assessment is really critical for risk assessment. When it comes to the sustainable aviation fuel sector, Argonne has a number of key collaborations that are critical for our work when it comes to sustainable aviation fuel development. We already talked a little bit about life cycle analysis and the sustainability group. Argonne is the creator of this GREET model that, as I mentioned, can evaluate greenhouse gas emissions, water consumption, various aspects of processes from cradle to grave is what we say. So that basically means from start to finish of an entire process and all of the steps throughout that process. There are a number of pathways. As you see here, there are 24 eligible pathways that are built into the GREET model. So there are a lot of opportunities, to assess the viability of different pathways and kind of the best way to maybe go about things, and also the impacts that various processes may have within these pathways. In addition to life cycle analysis and sustainability, Argonne also has a portfolio of multi-physics-based computational research. Here, this is essentially thinking about how we can simulate. If you want to think about, in some cases, adding biofuels into conventional engines, we need to be sure that these fuels are going to burn, that they're actually going to perform in the same way that conventional petroleum-based fuels would perform. Often it's not realistic to do all of that, experimentally in the lab. So this is one area in particular where computation plays a very critical role, because we can actually use simulations to kind of simulate that and then also analyze properties. A couple of other things here. You see this farm to flight, which I heard Kelly talking about in the beginning as I walked in. So this is actually one of one of our case studies that we've been developing. And then just something else that's kind of something interesting and nice to note is that recently in 2021, there was actually a flight powered by biofuels that went from the US, I believe, to Europe. And one of our Argonne researchers was actually on that flight. He is the one of the key personnel that was responsible for developing the GREET model. So because of his role in that, he was able to be a part of that flight. I'm running a little bit low on time, so I'm not going to go into this slide in detail. But again, this is just kind of showcasing some of our work related to opportunities for sustainable aviation fuel when it comes to biomass. So you can see some of the key points on the left-hand side here. There's definitely an opportunity for biomass when it comes to sustainable aviation fuels. And it's been estimated that biomass can fully supply the future aviation, marine, and rail sectors. But the biggest market pull is really in sustainable aviation fuels. That's really the biggest driver here, and so that's where a lot of our efforts are focused. DOE currently has 3 large-scale sustainable aviation fuel demo projects, and that provides the market for current ethanol production. In addition to that, we are supporting, decarbonization of chemicals. One thing that I did not mention in the beginning is sometimes in order to offset the lack of economic viability when it comes to sustainable fuel production, we'll often try to produce co-products. If these co-products have a high value, they can be used to offset the costs of biofuel production. And so supporting decarbonization of chemicals can be done in conjunction with biofuel development. That's something that's really, really important to consider because these bioproducts can offset sustainability implications, and they can also offset costs. A couple of highlights from our projects. I've mentioned to you the GREET model. The GREET model is a very widely used tool, nationally recognized tool that is used for evaluation of life cycle impacts. It is available for public use. So if you're interested, there are a couple of there's an online module that can be used. There's also an Excel spreadsheet-based version that can be downloaded that anyone can use to evaluate this. I talked a little bit about some of our water quality and water resource analysis tools. We have 2 different models that are kind of developed for that. We are working on process development and scaling up of various bioenergy technologies office when it comes to circular economy. This is, again, trying to take essentially waste products and turn them into something that has value, repurposing products at the end of their life to create something that is useful. We talked a little bit about process development. So process development may refer to things like conversion processes, for example, fermentation or anaerobic digestion. We have 400-liter fermenters that we are, kind of going from small scale, less than a liter or so, all the way up to 400 when it comes to process development and scale up. And then Argonne does have a lot of expertise when it comes to separation technologies. So you can just see some of the logo from the right-hand side, some of the projects and some of the efforts across the bioenergy technologies portfolio that Argonne is participating in. So with that, I'm going to stop there, but I would be happy to take questions. I'm sure that there are tons of questions, so I would be happy to answer anything that might be on your mind.
Question.
Sure.
So going back to your vision statement, very innovative and inspiring. However, I don't see anything about environmental justice in all of this.
Mm-hmm.
So is that a part of your vision and mission statement and considerations when doing all of these processes?
Yes. That is incorporated kind of on a case-by-case basis. So I think that's part of the reason that it's not incorporated in an overarching category here, but it is most definitely included on a project-by-project basis. I think for different projects that means something different. Whether we are thinking about the, end population of maybe the technologies or the processes that we're developing will impact, or, if we're thinking about where resources may be pulled from. But yes, that is definitely a consideration. I think that it's still difficult for us to find very concrete ways, either to quantify that or, an overarching way to incorporate that at a more broad level, but it's certainly a consideration.
I asked the question because that's what students ask.
You're okay.
They ask those questions. And also, are you working with like a third party, like a tribe for indigenous communities, to help you to like maybe his art lens doesn't see that? What might be detrimental to environmental degradation or something, or injustice? I'm just wondering if you partner with any other like social justice organizations or communities.
The topic has come up. This is, a relatively new focus area within the office, within the Department of Energy in general. So I think again, it's loosely defined how exactly that should be incorporated. I can kind of give you the counterexample that currently a lot of our projects at the beginning, when we're thinking about how we can design research and development projects, will actually go to industry. And now we're kind of broadening that. Instead of just going to industry, we're kind of broadening the audience in which we're eliciting feedback from, and how to design and what considerations should be taken into account. Very similar, like industry would say, well, we want you to minimize the cost. So when we bring these other stakeholders to the table to kind of, share their opinions and share their thoughts, then we can incorporate that kind of from the beginning when we start to have new projects that are under development.
Thank you.
Are your slides available later? Just like that?
I can make them available.
That'd be helpful.
That'd be helpful.
Because you have a lot of good diagrams that could be.
Sure. Yeah.
So I teach a clean tech course, and revamping it is, do you have modules already created? So I'm not reinventing the wheel, that we can borrow from you and use for
So
all of what you're saying here?
I think for some of it, I think Kelly may be able to provide a more broad answer. I can talk specifically what we're doing in Separations Consortium.
You talked about that.
Yeah. Okay. So this is something, it's very kind of near and dear to the project that I'm working on. One of my responsibilities here is that I lead a collaborative project focused exclusively on separation technologies that involves 6 national labs. In that project, we have a very dedicated and explicit outreach component, in which we have the 6 national labs. I'm going to go back to the map so that I can show you the map again. We have 6 national labs that are involved, and each national lab has actually been working with local community colleges. So we have PNNL here, Lawrence Berkeley National Lab, NREL here, Oak Ridge, Argonne, and then I think I've got 6. Oh, Los Alamos is the 6th one. So we have those 6 national labs that have each paired with local community colleges. With local community college instructors, each of these 6 labs is actually developing teaching modules and lessons about bioenergy. So those modules, because the audience there is community college students, we are actually going a little bit more broad than just separations. There are some modules that are more broadly focused on bioenergy. What is it? How can we use it? One of our modules, for example, the module that Oak Ridge National Lab is developing, is focused on machine learning and computational work. So we are developing these modules to be deployed and co-instructed with National Lab staff, and then also the instructors at the community colleges. The plan for those, we currently have 6 modules that have been developed. At least 2 of them have already been co-instructed at colleges near NREL and colleges near Argonne. So all of these modules, in the end, we will have 6 modules that kind of cover the spectrum. But again, it's not only separation technology, it's bioenergy in general, and also the various aspects from chemical principles, physical principles, biological principles, and even computing. So I'm really, really excited about that one. We should have all 6 modules that are available for public sharing sometime in the near future. That's part of our plan. Last year, we actually did a virtual workshop. So I can tell you that we do have, let me see if I can show you this. We do have some information that is available from our virtual workshop that we did last year. The website here is bioesep.org. And here there are actually some workshop materials that are available on our box folder. There are video recordings, slide decks, worksheets for some interactive activities. So this was actually this was our initial pilot year last year. We did this last summer for 4 summers. And now we're transitioning to the in-person model where each lab actually, goes to local community colleges.
What was that website again?
Bioesep.org. BIOESEP.org.
Say again, please.
BIOESBIO, like Edward. Yeah, energy. SE, like energy. P, like purple. I think Kelly's going to write it for you.
Sweet. Very good. Okay. Talk through. That's awesome. Nice work. I'm really glad Lauren got the chance to tell you about that, because indeed, you're here for this one project, but we actually have 3 projects in workforce development on bioenergy. So if you like what you see here, but wait, there's more. They're all a little bit different. So Lauren just told you about this one. Fantastic project. And there's also one that's focused around, basically there's like an undergraduate conference that people can come to. I'm not sure where it's going to be held yet. But now that you're here and you're part of our network, you're going to get these opportunities coming your way for the benefit of you and your students. So,
Is this for students, the undergraduate
yes, that's it.
I think when we did it in March, we had students come from all across the country. There were panels, scientific panels, career panels. Students had the opportunity to have lunch with a researcher, just to ask anything about career development, college, graduate school programs, anything that was on their mind. So, yeah.
So next week I'm going to the Circularity Conference that's here in Chicago.
Okay.
Are you going to be presenting? Is Argonne Labs going to be there presenting at all?
I am not going to be there presenting. I don't know if there's anyone else that is going to be. Is it a technical conference or?
It's through GreenBiz.
Okay.
And circularity. They have different tracks.
Okay.
Like transportation, material, lots about material.
Okay.
And life cycle assessments.
Okay. Okay. It's possible. I'm not familiar with it, but it's possible that
That would be perfect to be there to maybe. And
They're going to get to meet Axel Farrow tomorrow.
Okay, great.
Maybe. Yeah. He's in charge of our circular economy initiative here at Argonne. So, have to ask.
In any of these publications, like on the site, bio,
Yep.
can you suggest some? So, for advanced courses, it's good to teach them about semi-permeable and permeable membranes and separation as such, and bio-based versus not, polymer-based. And would there be something on it?
I don't think there's any materials on this website. I have given guest lectures. Actually, I gave one for a Northwestern course on chemical separation. So I have a slide deck that's on that. If you'd like me to come and maybe speak to your class or something like
Is
that.
your email
Sure, I can.
I mean, the students would love that.
So many of our scientists here, like Lauren is a special, exceptional example of this, are very engaged. They would love to speak and talk. And so we can arrange for virtual visits for classrooms. We have a number of volunteers that they're just waiting to be asked. So keep us in mind, okay?
Yes, I think that is definitely true. There are a lot of researchers that would be happy to speak to students. And I think it's dual benefit. It's also in some cases helpful for us. It's helpful as a recruiting mechanism for us as well. So we are more than happy, often than not to speak at your classes if that's of interest to you. Yes.
Can I ask a question about your presentation?
Sure.
So, you initially started off with carbon footprint, the amount of greenhouse gases. Perhaps I missed it, but what's the connection, or what is the savings that you get by combusting bio-derived or sustainable fuels as opposed to using fossil?
It needs to be evaluated on a case-by-case basis because there are so many different potential pathways or routes in going from biomass into to biofuels and bioproducts. The number that I showed on the slide was kind of a general calculation of basically taking all of the billion ton resources of biomass and waste resources that are available in the U.S. With that, if we produce bioenergy, biofuels, bioproducts, we could reduce carbon emissions by 450 million metric tons per year. I can't remember what percentage that is off the top of my head. But so it really also needs to be evaluated on a case-by-case basis. Because in some cases, we really need to consider processes holistically. We need to make sure that we're comparing on an apples to apples basis. For example, system boundary is the same in both cases, so it's really hard to give you a very specific number when it comes to emissions reductions.
Is that mostly in the derivation of the fuel, or because do you know that if you burn one like fossil fuel, same unit with renewable, like is there a savings in terms of carbon emission?
I mean, that's a very, the energy content of fuels is one of the first calculations that we often do in order to make sure that if we are going to try to produce energy out of a certain crop, that the energy density is sufficient enough to make a difference. I can tell you as far as contributions to the process, the reason that I work on separations in particular is because the separation step of bioprocessing, actually any chemical process, can account for anywhere, 60 to 80% of the total processing costs. So again, I'm giving you the number for cost because that's what's out there in literature. But the reason that it's so cost intensive is because it's extremely energy intensive. It's energy intensive because by and far, the majority, up to 80% of separation processes are currently thermal based. Because they're thermal based, they require that phase change. That's why they're so energy intensive, cost intensive. And that same energy intensity corresponds to the greenhouse gas emissions. That's why we need research and development on new separation technologies. The bioenergy technology's goal is 70% emission reductions. So we are not quite there yet. We are certainly not there when it comes to 70%. I can give you, a couple of examples of pathways that we've evaluated within our BETO funded projects. We are struggling to get to 70%, but it is possible in some cases. It just requires a combination of innovations. You can't just innovate the separation aspect, just like you can't only innovate the fermentation, or you can't only make improvements to the catalyst portion. Everything has to be considered holistically, but it is possible for us to start approaching that 70% marker. It's just not, it's not where we're at currently.
On your list of partners, I can't remember. Did you list the Carbon Disclosure Project? I know they changed their name, but that would answer your question about cost. Are you familiar with the Carbon Disclosure Project?
No.
Oh, they do all of the cost analysis and stuff. Okay. Okay. They changed their name, so I'm not sure what it is right now. Okay. But they go heavily into the costs of all of this technology. It's same with like what you just said, all of the systems and recycling is the same way. It's so energy intensive that it's not reducing emissions when we're recycling.
Exactly. And that's why things really need to be considered holistically. It's also why there's been more of an emphasis on waste to energy or waste to products. Because if we can take something that's essentially considered a waste product that is at its end of life, has no value to begin with, and we can convert that into something that has value, then maybe there's an opportunity there. But another thing that I want to point out is that having materials that are, for example, like biodegradable is not necessarily the same as having something that is like fabricated from a biomass source. A lot of times those two concepts get confused in terms of sustainability, but just because something is made from sustainable biomass resources doesn't automatically mean that it's biodegradable. Actually, our goal when we're producing, we talked about these drop-in fuels and chemicals and polymers that are essentially functionally equivalent to the petroleum-derived materials. That's often our goal. And so making something that is actually biodegradable or recyclable is an entirely different category and set of requirements.
So you said your research is about separations process. So does that include the distillations and refining for the SAF or any other biofuel?
So I don't focus on distillation for the sole reason that it is a major energy contributor. The technologies that I work on are pressure-driven membrane separations and electrochemical separations as alternatives to distillation because they can provide that lower energy. For example, membrane technologies can provide 90% less energy intensity than than distillation or thermal-based processes. So really focus on the alternatives.
So is it a commercial technology or still like development?
Pressure-driven membranes are their commercial technology. It's actually the dominant technology when it comes to desalination. So it has kind of overcome distillation when it comes to water treatment and desalination approaches. Unfortunately, the same has not yet happened for bioprocessing. Bioprocessing streams are a little bit more complex. In general, the bioprocessing industry is a little bit less mature. So there's more work to be done, more research and development to be done. But that is something that we're actively working on, these specific challenges.
I want to thank you so much for coming today. Thank you.